Chloe. Glad you could join me today. I've been looking forward to diving into this fascinating study about the Casimir torque between cholesteric DNA stacks.
Yeah, Liam, it's a really intriguing topic. I mean, the idea that quantum fluctuations can cause a twisting force between DNA molecules. Who would have thought?
Exactly. So to kick things off, let's set the stage. The Casimir effect is this subtle quantum phenomenon where invisible forces arise between objects because of fluctuations in the electromagnetic field. It's like an invisible push and pull caused by virtual photons popping in and out of existence.
Right, and what's really cool is that these forces aren't just about attraction or repulsion. When the materials involved have directional properties, what we call anisotropy, they can actually experience a torque, a twisting force. It's like the materials are trying to rotate and line up with each other.
Yeah, I like to think of it like two twisted gears sitting close together but not touching. The Casimir torque is this invisible force that tries to rotate those gears so their teeth line up perfectly.
That's a great analogy. And in this study, they're looking at DNA molecules arranged in a special twisted structure called the cholesteric phase. So DNA isn't just the blueprint of life. It also has some pretty interesting material properties.
Absolutely. Under certain conditions, DNA molecules can organize themselves into liquid crystal phases. The cholesteric phase is one where the molecules form a helical or spiral pattern, kind of like a twisted staircase. This chirality, or handedness, means the structure twists in a specific direction.
And that twist is what makes the DNA stacks anisotropic, which is essential for the Casimir torque to show up. Without that directional difference, you wouldn't get this twisting force.
So to study this, the researchers used what they call a spiral staircase model to capture the helical geometry of the cholesteric DNA. They also applied the Rayleighmethod, which is an effective medium approximation, to model how the DNA cylinders pack together in a hexagonal pattern.
Right, and the whole setup is DNA stacks embedded in water and sandwiched between silica substrates. Silica is a common material in biomedical devices, so this setup is pretty relevant for real-world applications.
What's interesting is that the model accounts for both the shape of the DNA stacks, what they call morphological anisotropy, and the material properties, or dielectric anisotropy. So it's a pretty comprehensive approach.
Speaking of dielectric properties, a key input for calculating Casimir forces is the dielectric function, which basically tells you how a material responds to electromagnetic fields across different frequencies.
Exactly. And in this study, they compared two dielectric models. One is a bulk DNA dielectric function, which is a general average property, and the other is a more specific model for an adenine-thymine, or AT, 10 base pair oligomer. This AT10 model is based on ab initio calculations, so it's more realistic for specific DNA sequences.
That comparison really highlights how sensitive the Casimir torque is to the precise molecular composition and structure of DNA. It's not enough to just use a generic bulk model.
And that leads us to one of the key findings. The Casimir torque between the DNA stacks depends on the angle between their orientations and the distance separating them. The torque varies sinusoidally with the misalignment angle, following a sine function of twice the angle.
So basically, the torque tries to rotate the stacks into alignment. But here's the kicker. The torque amplitude for the AT10 oligomer is more than 4 times larger than what the bulk DNA model predicts at the shortest separation of 25 nanometers.
That's wild. It really shows that realistic modeling of DNA's dielectric properties is crucial for accurate predictions.
Another surprising result is the persistence of finite-thickness effects. Even when the separation between the stacks is much smaller than the DNA film thickness, the finite size of the DNA layers still significantly influences the torque.
Yeah, that challenges the common assumption that you can treat DNA stacks as infinitely thick in these calculations. The finite thickness really matters, even at very small scales.
Now, the calculations use something called Matsubara frequencies, which are imaginary frequencies that simplify the complex electromagnetic interactions. The lowest frequency term, called the n=0 term, often dominates the Casimir effect at larger distances.
In the bulk DNA model, this n=0 term accounts for nearly 100% of the torque at all distances, which might be an oversimplification. But for the AT10 oligomer, the contribution of this term grows with distance, from about 35% at 25 nanometers to 100% beyond roughly 487 nanometers.
That behavior aligns better with what we'd expect physically and highlights the importance of detailed dielectric data.
So Chloe, what do you think about the experimental challenges here? Measuring Casimir torque in biological systems like these DNA cholesterics sounds pretty tough.
Definitely. Especially in liquid environments, hydrodynamic forces dominate, making it hard to isolate the Casimir torque. Existing methods rely on pneumatic liquid crystals and can't directly measure torque between two cholesteric phases.
But the paper suggests that hybrid systems combining cholesteric DNA and pneumatic liquid crystals might offer a way forward.
Yeah, and understanding and controlling Casimir torque has exciting implications for DNA-based nanotechnology. Think about DNA self-assembly for complex nanostructures, targeted drug delivery using DNA nanocarriers, nanophotonic devices manipulating light at the nanoscale, and bioorganic nanoscale electronics and sensors.
It's a perfect example of physics meeting biology and nanotech. But the study also stresses the need for precise optical measurements of DNA's dielectric properties, tailored to specific base pair compositions to improve both theory and experiments.
So, to sum up, this research reveals that the Casimir Lifshitz torque between cholesteric DNA stacks is strongly influenced by the detailed molecular structure and dielectric properties of DNA.
And that torque can be significantly larger than previously thought when realistic models are used. Plus, finite thickness effects on chirality add complexity, but also opportunities for tuning these forces.
Future experiments and theory will help bridge the gap between idealized models and real biological conditions, pushing forward DNA nanotechnology applications.
It's fascinating to see how quantum electromagnetic fluctuations can influence biological macromolecules and their assemblies in such a tangible way.
Absolutely. It's a reminder that even at the tiniest scales, physics plays a huge role in the behavior of life's building blocks.
Well, thanks for unpacking this with me, Chloe. It's been a great conversation.
Likewise, Liam. Always a pleasure to explore these complex topics together. Until next time.